acid-base titration curves. So we did acid-base titrations. Who can tell me what they remember about doing an acid-base titration?
One thing makes the other thing, and the thing.
Mix one thingy with another thingy.
With acid, you get H3O.
Sorry, Sam? You have something to say about acid-base titrations?
No, it's about my pen.
Okay. Sorry, Ava, what were you saying?
Acids make that H3O.
Yeah, so acids make H3O plus, bases make OH. Who remembers doing a titration though? Now we're neutralizing. We did a lab of this. Do you remember, Brody?
Something like endpoint?
Yeah, something about an endpoint.
When it stopped, or when it got saturated with the...
Yeah, how did we know when to stop?
We put in the thing that made it change color.
When it changed color.
When it changed color. So we did an acid-base titration, and we stopped at the color change. And what happened at the color change? Like physically, with our chemical reaction?
It was a saturated.
Not quite saturated. But I think you're on the right
So
theme.
neutralized.
Neutralized, yeah. So we neutralized all of our acid. If we had the acid in the little Erlenmeyer, it was all neutralized, and we had just a little bit extra base in there. We're doing an acid-base titration. And the little bit of extra base did what with the indicator?
Made it change color.
Made it change color. So we could also do the same titration without an indicator. We could use instead a pH meter. And that's what we're going to look at today. They're really tedious because you add a little bit of your titrant, and then you measure the pH, and you measure the volume that you've added. And then you add a little bit more titrant, and then you measure the pH, and a little bit more, and etc., until you get a curve that looks like this. So we'll watch a little video on it first, and then I'll explain what our curves mean. So this is going to work for us.
A titration is a controlled action.
Get my volume fixed first.
Base neutralization reaction. 20 milliliters of hydrochloric acid of an unknown molarity is added to a flask. 2 drops of indicator dye are added to the acidic solution. This indicator dye is clear in acidic solution and pink in basic solution. The burette is filled with a sodium hydroxide solution of known strength, and an initial reading is taken. The base is added to the acidic solution until the solution stays a slightly pink color. At this endpoint, a final reading is taken. The moles of base added equal the moles of acid present. This same reaction can be followed using a pH meter instead of an indicator dye. Initially, the pH changes very little as base is added. Suddenly, the pH changes rapidly as the endpoint passes. The solution quickly becomes very basic, and again, the pH changes very little. The endpoint occurs at this middle point on the curve.
Okay, so that was an acid-base titration. So that would be kind of like this curve here. So we've got hydrochloric acid titrated with NaOH. So in our little Erlenmeyer, we've got our HCl. In our burette, we've got our NaOH. So if we're measuring the pH of the stuff in the Erlenmeyer, and we just have acid in there, what kind of pH would we expect? A low pH. So that's what we're seeing here. We're seeing a pH of 1. That's when we start, before we've added any base. Does that make sense? Okay, so we start adding base into here, and we still have extra acid left over. Should our pH still be pretty low? Yeah. Does it make sense that as we keep adding base, we're reacting that acid, neutralizing it, so there's less acid in there, and the pH is climbing up a little bit? Does that part make sense? Okay. Once we've reacted all of our acid, and there's no extra base in there now, so we've reacted all of our acid up, and it's just been totally neutralized. That's this point right here. Notice our pH is 7. So we've neutralized this strong acid. There's no extra base now. Does that part make sense? We keep going now, and we're adding more base in here. Does it make sense that our pH would be climbing? Yeah. And now we've got strong base in here, and that's kind of the end where we've added our strong base. So there's just mostly sodium hydroxide, and then our neutral salt, sodium chloride that we've made, we've neutralized it, and a lot of water. We've got a basic solution in here now. Does that part make sense? Take your silence as an affirmative. So the middle point of our spike here is called our equivalence point. So let's write our definition up here. So B's titration curve is used to accurately determine the equivalence point. The pH is recorded for each volume increment added, and that's what we plot. So that's how we get this curve here. We record well beyond the endpoint equivalence point, and then a graph of pH versus volume. Of titrant is made, and from this graph we can get the equivalence point. So far so good? We are going to do one of these in the lab. We don't have a pH meter. Bless you. Okay, so if we look at this graph, what do you think is the stuff in our Erlenmeyer? Is it an acid or is it a base? And what do you think is the stuff in our burette? An acid or a base?
The other one.
And why?
Because it starts
The
basic.
other one.
Perfect. So lots of people are saying opposite of the other one, or we have a base in here, and you're telling me that because we're starting when we haven't added any titrant, our pH is basic. So this is an opposite curve. So we're analyzing a base. We've got an acid titrant. So the opposite is happening. So as we're reacting at our base, our pH is slowly dropping. When all of our base has been reacted, we have pretty close to a neutral pH. Now we've got extra acid in there, and our pH drops. The opposite kind of curve is happening. So still the midpoint of this steep climb is our equivalence point. Cindy?
If we added sodium to water, would we get sodium hydroxide and hydrogen gas?
Yes,
Yes.
we did that in the lab. Yeah.
I don't remember.
Okay, so the midpoint of the steep pH change is called our equivalence point. After the equivalence point is found, a horizontal line to the y-axis will give us the solution pH at the equivalence point. Based on this pH, we can choose a good indicator. So we practiced picking indicators last week, or using indicators to figure out a certain pH. So we would want an indicator that changes color right around our equivalence point. And then we wouldn't have to make a tedious graph if we needed to do lots of these titrations. We could just use a nice indicator that would change color. For titrations of strong acids and strong bases, the pH is always 7, since the salt that forms is a neutral salt. So for example, sodium chloride is a neutral salt. So we don't have any compounds in there that can give up or take protons to change the pH of our water. So for example, sodium chloride formed from the reaction of hydrochloric acid and sodium hydroxide. So I was going to look at the molecular equation. So to see what's happening with our
What is that after molecular? What's that?
an equation, EQN for short, molecular equation. So to see why we don't have any acidic or basic compounds in solution, we're going to look at the molecular equation. It's kind of good review for writing our net ionic equations. So if we react hydrochloric acid, sodium hydroxide, what are our two products?
Water and NaCl.
Water and NaCl. Awesome. So now we're gonna work to writing a net ionic equation. Who remembers how to do that?
You gotta split up the ones that are aqueous.
Gotta split up the ones that are aqueous. Maybe I should put some states in here then.
They all are, aren't they?
They all are except for
Sodium chloride?
nope,
Water.
the water.
Alright.
So we're gonna split everything up except the water. So let's go to Michaela. How does our HCl split up? H plus, Cl minus. Let's go to Taylor. How does our sodium hydroxide split up?
So sodium and hydroxide.
Sorry, say that again.
Sodium hydroxide.
Yeah. Sodium cations, so Na plus OH minus. Let's go to Damien. Does water split up?
No.
No. So anything with the state, if you recall, of a solid, liquid, or gas is going to stay in molecular form. Now let's go to Reese. How does our sodium chloride split up?
Na plus Cl minus.
Awesome. Who remembers our next step?
And cross out the ones that are the same.
We cross out the ones that are the same. Katie, what's the same?
CL minus.
CL minus is the same. Na plus is the same. Thanks, Sam.
That's it.
And that's it. Nathan, what's our last step? Bless you. Bless you.
Put it back all together.
Yep, we write it again without the crossed out ones. So we've got H plus reacts with hydroxide to make H2O. So at our equivalence point, all of these acidic protons have reacted with the hydroxide, and the only thing in there that is of any importance is water. So neutral pH. So that's why for titrations with strong acids and strong bases, our equivalence point pH is always 7. That's not the same for our weak acids and base titrations. So we're going to look at those guys next. Okay, so what do we do with this titration curve? We draw a line straight down. So the equivalence volume can be determined by drawing a vertical line to the x-axis to figure out the volume that we needed to do this titration. Before, when we were doing this in our burette and an indicator, we measured our initial volume and our final volume, and we subtracted those two to get the volume added. So now we're going to read that from a graph. Does that make sense so far? Hopefully. Okay, let's do an example. So we've got a 25 milliliter sample of this stuff. It's titrated with 1.04 molar of this stuff. We're going to use a titration curve. It's on the next page to calculate the concentration of our acetic acid, which is this stuff. Are we ready? So this is kind of a stoichiometry problem. We already know some steps for approaching these. Yeah, write down our formula and everything that we know. So Ava, what are the two things that we're reacting?
NaOH and then CH3COOH.
Awesome. Sarah, what are two products that we're making?
I think you get them CH3CO. NaCH3CO. Maybe. Is that right? And then water.
Water. Which we could write as HOH to help us balance. Nathan, is this balanced?
Yes.
Yes. So we're all balanced. What do we know about the sodium hydroxide?
It's 1.04 moles per liter.
We know its concentration. What do we know about the acetic acid? We've got 25.0 milliliters. That's all our question tells us so far. What are we asked to figure out?
The concentration of the CH3COOH.
Concentration of acetic acid. So what did we usually also have here? Volume. So we're going to get that volume on our next page from the graph. So rather than doing an initial and a final burette reading, we're going to figure out what that equivalence volume is from our graph on the next page. So there's some steps to help us find what we want is the halfway point of this line here. So there's some little steps to help us find that. So step number 1, it's usually pretty helpful to have a ruler, but we're gonna draw, see how these two flat parts kind of make a plateau? We are gonna draw a nice straight line across that plateau part.
How far should you extend that line like you did?
Just a little bit on either side. So we want it extended so that we can draw a third line on this vertical portion right here. And we want it to hit in 2 spots. So we want it to hit our vertical line here and here. So our red lines should be extended a little bit. Kind of making sense so far? So the reason why we do that is because now we want to measure the midpoint of this line. So literally taking a ruler and finding the halfway. And what do you think that halfway point is?
Your pH is 7.
What's the average? I would say like the middle of the green line.
No, what's it called in general? Not where is it specifically?
Oh, the equivalence point.
It's the equivalence point. So that halfway point, I'm just gonna kind of put a guesstimate up here, is our equivalence point.
What do you put that? You put that at about.
So I'll show you exactly where it is, because I didn't measure with this at all. But I did measure on this graph here. It's kind of annoying that my drawing's still there. Oh, leave those lines up in this first thing. I'll try to match it up with those lines there. Pretty close. So we're at 9. So if you do that work with a ruler, you're gonna get our pH. Equivalence pH is pretty close to 9. Reading our scale, we get a little closer to 8.9. And dropping another vertical line straight down with a ruler gets us our equivalence volume of 21.38 milliliters. So far, so good. So Brody, what do you think we're going to do with this number now?
Figure out its concentration.
Yeah, figure out its concentration. So we can flip back to our previous page. Remember this volume that we were looking for? We now know it's, what did I say, 21.38. Now we have a nice little stoich problem with a Canooan, an uncanoan, balanced chemical equation, and we can figure out our concentration of the acetic acid. So Sam, what should our next step be? Close of no. Convert to moles of known. So which ones are known, Sam?
The one on the left.
The one on the left, the sodium hydroxide. Perfect. So we're gonna take this 1.04 moles per liter. This is of our sodium hydroxide. And I'm gonna be a lazy chemist, and I'm gonna leave my volume in milliliters. You can convert to liters if you choose. But I don't want to do more work. So I'm going to multiply by the volume of sodium hydroxide that we needed to add to react up all of the moles of acetic acid.
How did you get that volume?
From our graph. So we made this nice titration graph, so for every incremental volume, looks like they measured the pH for every milliliter. The pH was measured initially, and then they did, looks like every half milliliter, they measured the pH until they got this nice curve here. They plotted it, and then we used that plot to determine our equivalence point. Does that make sense, Sarah? So the equivalence point is where we've reacted all of our moles of acetic acid. It tells us our equivalence volume and gives us our equivalence pH. So right now we're using this number. So far so good? Alright, so Sam took us through our first step to find us moles of quinoa. Michaela, what's our next step? Moles of unknown. What's our strike ratio? 1 to 1. So for every 1 mole of acetic acid, we react 1 mole of sodium hydroxide. Katie, I'm going to you next. So moles of sodium hydroxide are gone. We've got millimoles of acetic acid.
How do we 0.05?
So we
Just leave it in milliliters.
Put the 25 milliliters on the bottom.
put the 25 milliliters on the bottom. Then our millis cancel out, and our units are moles over liters, which is what we wanted. So I'll let you guys crunch those numbers. So Sydney got
I don't know if anyone agrees with me. but that's what I got.
0.889
Yeah.
moles over liters, and that's of our acetic acid. Okay, so it's a stoic problem. Instead of, again, using an indicator with our initial and final volume of our titrant, we used a pH curve to get this 21.38 milliliters to get to our equivalence point. Sydney?
So the only difference is that we're getting the volume from a graph instead of measurement.
Easy peasy.
And now we can work on
It just adds a step, actually several steps. So we're not quite done. So in the lab, it would be more work because you actually have to take a measurement for every milliliter added rather than just an initial and a final. Is there an advantage to this, do you guys think?
More accurate.
It's more accurate. It's way more accurate. Our endpoint, our indicators change in a range. Remember we looked at those ranges? So if it changes between a pH of 8 and a pH of 10, we've got a bit of wiggle room there, right? So this is more accurate. Awesome. So we're not quite done because we're going to talk about why is this pH here 9? Why isn't it 7, like with our strong acid?
because it's allowed to be because that's what it is.
Excellent answer, Katie.
I feel like it. That's
Because it doesn't start as strong?
Not
Yes, it doesn't
quite.
start as strong?
Not quite. Let's look at our,
Are you gonna tell us the answer?
I'm going to tell you the answer. I should have left room for this somewhere in here.
Yes, until we get it.
We're going to go to this for our answer.
Freaking black looks sharp.
Betty, you're enjoying the black.
Blue in there too.
Okay, we're gonna look at this. Oh, I'm gonna do blue next. Good call, Sydney. Remember we were looking at lots of our salts And when we put them in water, sometimes they make acidic and sometimes they make basic solutions. So this is our salt that forms. So how would we figure out if this is an acidic or a basic salt?
It's basic because it says that.
It's basic.
We could test the pH, so we could do an empirical.
It was higher than 7, so it's basic.
Okay, so we did test the pH from our curve, but let's use our modified Arrhenius theory and write the ionization equation. So how does this thing react with water to make that water basic?
Well, it needs an H. Doesn't have
It creates OH. So let's look at how it does that specifically. So what were our steps for doing that?
You need to break it up.
We need to break it up. So we're going to take this. Oops. There's no H there. And I already hear some of you talking about what we ignore. So we make sodium ions and acetate anions. So why do we ignore the sodium ions?
No, we always ignore
It's a
them.
metal.
It
It doesn't make H3O or an OH.
It doesn't make H3O or OH. Michaela? Yet group 1 ions don't react with water. Damien?
Missed C,
And Damien's catching my mistakes.
Shouldn't there be an O on the other one too? I mean, a C on the other one?
Yeah, you missed it on both sides.
Yeah. Awesome. I'm gonna just squish it in here. Is that better?
I mean,
Okay, so remember when our substances react with water, they either steal or give up protons. Protons are pluses. So could sodium attract a plus to it? No. Does it have a plus to give, an H plus to give? No. So that's why we ignore it. So we're going to look at what this thing does with water.
Gives its H's.
So it's a little bit confusing. Lots of our organic acids are. These H's aren't acidic. So they're covalently bonded to carbon. They're pretty happy where they are. Carbon would be very unhappy if any of them left. So it doesn't have any H's to give up. It's a little deceiving.
So it snatches the
So it's going to snatch the H because it has that negative charge right there. So we're going to draw what happens when it does that. So it reacts with H to the iso. It snatches an H. What does it become? So the water loses an H plus. Brody's telling us that it becomes hydroxide.
It's CH3COOH.
And we make CH3COOH. Awesome. So the fact that we've ionized water to make hydroxide ions tells us that this is basic.
Is there not a rule you can use to like is there no generalizations that you can just use to know if it's basic or acidic? Or you have to go through this process?
There are. We look at them in great detail in Chem 30. We go through this process right now, and we do have in our data books. Where did I put our data book? Did I not save it with the data? Nope, I did not. Oh no, it's right here. So in our data books, we have our list. Remember on the left column, these are all of our acids. These ones are strong. So we know those for sure make H3O plus with water. Their anions here are not good bases. So these are neutral anions. We've got a whole list of weak acids. And then last class we looked at this list, our right-hand list. What are these ones? Bases. These are all of our weak bases. And if you look, I think acetate's in there. here. So it's going to react with water, just like we showed, to make acetic acid and hydroxide. So Sarah, if you're looking for a nice, easy way to do this, you can use this data table. So if your ions are on the left here, they're going to be, as Brody said, snatching an H to make an acid, or to make the anion, whatever it is, and hydroxide ions. If you see a thing on the right, it's going to be combining with water to make an anion and H3O+. So you can use your data table to help you with these ionization
So
equations.
H3O plus is produced in an acid?
Yeah.
And OH is produced in base?
Yeah. So that's our modified Arrhenius equation, or Arrhenius theory, a modified.
So why is there a modified one and a non-modified one? That's confusing.
Yeah, it is a little confusing, our curriculum. It steps us up. So next year in Chem
So
30,
we don't have to worry about the not modified one?
this is our modified. Our not modified doesn't work. So our Arrhenius theory says that if we have hydroxide in our equation, in our formula, it's basic. If we see an H plus in our molecular formula, it's basic. So then Y is, for instance, sodium acetate, basic. There's no hydroxide in that chemical formula.
Oh, okay.
That's sodium propanoate. It's because of this reaction, right? Does that make sense?
Not really, but okay.
Okay, so all of that to help explain why our equivalence pH was not 7. So when we react weak acids or weak bases, we're going to get equivalence pHs that are not 7. So far, so good. So we're going to look at a few more titration curves and then talk about picking indicators to do a titration. So before we look at, oh no, we can go through this. So for titrations of weak acids and bases, the pH at the equivalence point is not 7. So why is this? This is because our neutralization salt that we make reacts with water to form either hydronium or hydroxide ions. So we looked at that with our acetic acid and sodium hydroxide titration. Does that make sense so far? Okay, so we already looked at, oh, I guess I did make space for this. So we looked, no, we didn't look at this one. We're going to look at the neutralization reaction between carbonic acid and sodium hydroxide, write a balanced reaction, and a net ionic equation. All right, so what are we reacting for our balanced chemical equation?
2 thingies there.
Those 2 thingies here. H2.
I like that you actually took that as an answer.
CO3 plus NaOH. Damien, what's one thingy that we make?
One thing that we make would be water.
Make water.
You always do actually.
Ava, what's another thing that we make?
NaCO3.
Yeah, sodium carbonate. How many sodiums and how many carbonates?
Is it Na2CO3?
Yeah, because carbonates charge is 2 minus, and sodium is 1 plus. Okay.
And then we're good.
So
There
total ionic equation, we're gonna
It's
break.
not balanced. Miss
Oh, it's
Wexler.
not balanced.
You need a 2 in front of the base and a 2 in front of the water.
Okay, 2 in front of this guy and 2 in front of this guy.
There you go.
That looks better.
Jeez.
Jeez. Good thing you're here, Sydney.
I'm so disappointed.
You should be.
So now we need to break up the ones that are aqueous.
Need to break up the ones that are aqueous. Awesome. So remember, our weak acids and bases we don't break up.
Oh, we don't?
This is a weak electrolyte. So this is going to stay as a whole molecule. Now we're going to break up our strong base. We've got 2 sodiums and 2 hydroxides. We're not going to break up our water because it's liquid. But we've got an ionic compound, so we make 2 sodiums and 1 carbonate.
CO2 is a minus, right? 2 minus.
Yeah, CO3 is 2 minus.
So you only get rid of the sodium.
So we only get rid of the sodium. That's our next step. Cancel our spectator ions. This guy's watching. This guy's watching.
It's actually the same guy that's watching.
Same guy that's watching, yes. So in total ionic, or net ionic equation, we write what's left over. We've got carbonic acid reacts with 2 hydroxide ions to make 2 waters and 1 carbonate.
This is probably a dumb question, but why didn't you break apart the first one?
It's not a dumb question, it's a good question. Does anyone remember why we didn't break apart our first thing?
Because we don't break apart weak thingamajiggers because they thingy less than 50.
Yep, they only dissociate a very small amount. So we don't break apart our weak electrolytes. Do we have to memorize weak electrolytes?
No,
They're in our tables, yeah. So these are
Weak
all,
electrolytes are the ones.
all of these weak electrolytes. These are basically all of our weak acids. And carbonic acid is in here somewhere.
Oh, yeah, H2CO.
There
Okay,
it
so all the
is.
ones below hydronium ion are weak electrolytes?
Yeah, all these guys are weak. And all of these are weak bases. So they're going to stay as whole molecules if we're dissociating. Okay. So let's talk about the pH of this stuff.
Is it still the same equation? It's on the second page. So the next page. Is it still the same thingy?
Nope, different thingy on the next page. Choosing acid-base indicators.
No, this graph is on the next page. I already did this. This graph.
Yep. So this is the graph on the next page for you guys.
Okay.
So before you turn to the next page, let's talk about the pH of our reaction when it's all done.
Hold on.
Hold on.
You said before you turn to the next page. Oh, so we're not on that page.
We're not looking at the graph yet. Not quite yet. So far so good? Okay, so let's talk about the pH of this reaction when it's all neutralized. Will it be acidic? Will it be basic? Will it be neutral? And why? Nathan, what do you think? Couldn't tell me.
It will be acidic and basic.
It'll be basic?
Yeah.
Why do you think it'll be basic?
Because on the graph it ends basic.
Perfect. So looking on the graph, we can see that it ends, our equivalence point here is pretty basic. Cool. What about how this guy might react with water?
How does it take the H's?
Brody says it takes the H's.
So then we end up with OH.
So we end up with OH. So we're gonna we're gonna write that out. So that's what happens right here. This carbonate.
So now do I go to the next page?
Sure, you can go to the next page now. Reacts with water. I'm gonna pick on Nathan again. What are products here when carbonate reacts with water?
CO and then OH. CH.
And what's your other one? So this thing's not gonna lose O's, it's just stealing an H. So it's gonna be HCO3. What's its charge gonna be?
I said backwards.
Damien says it's negative. Do you agree with him?
What did you write?
Yeah.
It's HC.
Perfect. So basic. So remember last class we talked about polyprotic acids and bases? What does that mean?
I don't remember.
Yeah, more than one proton that can react with water.
Yeah,
So
that's
if you
what
look
that
at
So
carbonic acid, how many protons does it have to react with water? Or to react with a base? It's got 2. So that's why when we do a titration
there's
of
two
a
thingies.
polyprotic acid, we're going to get this equivalence point when we have taken 1, we'll just say plus OH minus. We've neutralized 1 proton. Right, we've taken just 1 of carbonic acid's proton to neutralize it. And then this is going to continue to react in our second titration here. So we've got HCO3 minus reacting with the base to finish this off to make water and carbonate. So our polyprotic acids and bases will see potentially 2 or 3 little equivalence points.
Wait. Why are we adding?
So this is the reaction here to get to that equivalence point.
Why are we adding hydroxide instead of?
Because we're titrating with hydroxide. And this is the reaction to react the last proton at our second equivalence point. So we've got 2 little mini reactions that happen here. Is that making sense, Reese? Yeah. Okay, switch to the next page. Okay, so a few more titration curves to show you kids. So we've got our strong acid titrated with a strong base. Its equivalence point will be right at 7 on the nose. If we've got a weak acid titrated with a strong base.
We don't have that.
I know you don't. I'm just showing you some more curves. Our equivalence point won't be at pH 7 because we have that salt there that continues to react or ionize with water. So that's just showing the difference between strong acids and base titrations with weak acid base titrations. Got another curve for another polyprotic acid with a strong base. This one is phosphoric acid. So we've got 3 protons. So that's why there are 3 equivalence points. So just some potential pH curves that you'll see. last thing we're gonna talk about, you do have this, is choosing an acid-base indicator. So stay with me, Michaela. We're almost done. So since our pH at the end point or equivalence point can differ for various acid-base titration reactions, we must take care to select the correct acid-base indicator. We want the indicator to change color where the pH changes at the equivalence point. So, for example, our equivalence point is right here on this graph. Maybe I'll use a different color that'll show up. So right here. So if we used bromophenyl green, it changes color in this pH range between 3 and a bit, 4 and a bit, 4.5.
That's like 5.
Oh, sorry, 5.
By
Yeah.
2.
So between 3.5 and 5. So we'll get a color change. That is well before our equivalence pH. So this would be a really bad indicator to get. What about bromophenyl blue? Also not changing color where we want it to. A good one would be phenolphthalein. Does that make sense? All right, so I think we're done. We've finished our unit now as well. So rest of class, we're gonna finish up your assignment. You can now answer the last question. You've got some practice in your textbook, and then I think I put in your course pack review questions. No, I didn't. I'll come up with some review questions for tomorrow. So we'll review tomorrow and then unit test on Thursday.